Hello everyone, I am Shobhande, teaching assistant of EE6108 Advanced Electrical Machine Design and research scholar of Electrical Engineering Department of IIT Bombay. So today in this video we'll learn that how to optimize a electric motor that is designed in ANSYS electronics desktop with the ANSYS Maxwell package with the help of ANSYS Optislang package. So for that I have taken a surface mounted permanent magnet motor model, you can see here, and I have kept this project in a separate folder, in a clean folder I have kept this project. Okay, so this is my motor model. First, one thing to notice that for optimization, if I want to change the rotor mmf, I have to change the dimension, that is the geometric dimensions of the permanent magnet in the rotor. Now, if I want to change the stator mmf, I have to change the ampere turns. So the current per turn in the stator slots and the number of turns in the slots. Now, if I want to optimize the geometry, so my stator ampere turn has to be a function of the stator geometry, specifically the function of the stator slots. So to do that, first we have to go to Maxwell 2D design properties. I have already done it, but now I will explain to it how I have done it. Okay. So first we have to define the area of one slot. Now you see here the slot area, the slot area where I can accommodate all the conductors is this area. This area. It is a combination, for this case, it is a combination of a trapezium, that is this thing. This is a trapezium and a half circle. Okay. Better I can draw also. So this is our slot. This is our slot. Okay. This portion is for wedge, so it is not for winding. So here I can accommodate winding. Now up to this is a trapezium and this is a half circle. Now this length is bs1, this length is bs2, and this height is hs2. Okay, as I have said in my earlier video. And the radius of this half circle is, if this is bs2, this radius will be bs2 by 2. Okay, so accordingly we can define the area of the slot. So yes, this is as. See, as is bs1 plus bs2, bs1 plus bs2 by 2 multiplied by hs2. So this is the area of the trapezium plus 0.5 pi bs2 by 2 the whole square. So this is the area of the half circle. So this is combinedly the total area of the slot. Okay. Now the whole slot area is like doesn't occupy the copper, it will occupy insulation also. Not only that, there will be gaps, so air will also be there. So what would be the effective copper area? That we can define by KCU, that is copper fill factor. I am considering here is 0.4, that is 40% copper fill factor. And in addition, we are defining delta S, that is stator surface current density. 6 is 6 ampere per millimeter square. You can see all the things are without any unit. I have defined like this. Okay. Now, based on this, what will be my current? This is the expression of my current. So AS is the area of slot multiplied by KCU, that is copper fill factor. So this much area of copper will be there by 2, means there are 2 layers in one slot. I am considering one layer. So that's why by 2 multiplied by delta S, ampere per millimeter square. Now this AS, that is the area of slot is in meter square, but delta S in ampere per millimeter square. Therefore, I have to multiply it by 10 to the power 6. So combined, this thing will give me the ampere per half slot. Okay, so ampere in per slot per layer. Okay, and in one layer there are TC number of conductors. Therefore, combined this expression will give me what would be the current per conductor. Okay. Okay. Now, so this phase current or current per conductor, phase current, why it is phase current? Because I have considered that all the conductors are connected in series. So the phase current is now a function of the geometric parameters. Okay. So if I change the stator geometry or the slot geometry, my current will also be changed. Okay. This is one thing. Second thing is we have to define what is the stator copper loss. Now the copper loss is I square R and R is rho into L by A. So see W CUS copper loss is equal to I phase square into R phase. Okay, and further we can write equal to rho into L empty. The mean turn, there is the turn of like length of one turn, rho L by A. This is R multiplied by I pH square. Okay. Now see, take one IPH from here and by A. So it will give us equal to delta S, that is IPH by A multiplied by IPH multiplied by rho multiplied by LMT. Okay, so this is our expression for the stator copper loss. Okay, so we are doing that only. See here, rho I have considered here for 100 degrees Celsius. Actually, we have to do thermal analysis to get what a closed loop thermal analysis to get what temperature it would be. But for this time, I am considering for this simulation, I am considering 100 degrees Celsius. So that is 2.2 into 10 to the power minus 8. This is the resistivity of copper, and LMT. So how I can calculate for a, this is a distributed winding and double layer distributed winding. So I have considered a empirical equation, standard empirical equation. I have taken it from the book of MG Say. It's a renowned, very old book. So I am explaining what I have done. L here is the stack length, as you know. 0.95 is the stacking factor. So L by 0.95 is the total length. 1.15 is a factor in that empirical equation. Now pi d by p. Pi d is the circumferential length of the bore by p, that is circumferential length per pole. Okay, so this is the linear length of one pole pitch. Okay, plus 120 millimeter. This is the total empirical equation. Okay, now we know that QS number of slots are there in the motor. By 3 means uh, per phase there are QS by 3 number of slots. Okay, multiplied by 2 for 2 layers and multiplied by TC. That means TC number of turns are there per layer. So combined these expression will give us the total length of one turn, considering, as I already told, that considering that all turns are connected in series, so this would be the total length per phase, length of conductor per phase. Okay. Now, then what would be the WCUS? It is the loss 3. Okay, so this is per phase. Okay, I have not multiplied here 3, so this is per phase. For 3 phases, I have to multiply 3 here. Okay, so 3 delta S. Yes, 10 to the power 6, because I have defined the delta as ampere per millimeter square. So 10 to the power 6 IPH rho 100 LMT. And unit type is power, unit is watt. If you do that, so it is for this timing, it is around 250 watt is the stator loss is coming. Okay, so all these things only I have to uh, do for to start the uh, optimization, or at least this optimization. The idea is here that whatever parameter we are going to optimize, if some parameter related to that, some subsidiary parameters related to that are there, then all those things has to be calculated, or all those things has to be expressed in terms of the all geometric parameters that are going to participate in optimization. Okay, this is one thing. Second important thing is, first we have to simulate it. Validation check, it's fine. Analyze all. Okay, simulation is done. Check the result first. Here transient report, rectangular plot, torque, moving on torque, new report. Check the average value. Set average 14.63, it is fine. Again, also check the terminal voltage of 3 phases. Yes, it is fine. Okay, no problem. So the simulation is running properly. Okay. Now, one thing is, um, remember that for the optimization, that to couple with Optislang, you need to delete all these transient reports. Okay, just delete them. Right click, create transient report, data table. You have to create data table here, not plot, data table. So for this tutorial, I will show you that like for this file, we'll do uh, we'll optimize efficiency and torque density. Okay, a very simple or very fundamental thing. So for that, I need torque. So you have to write here AVG, that is average of moving on torque. Okay, new report. So you can see that average value of torque is added here. Now to calculate efficiency, we need output power also. So average of torque multiplied by our speed is 1500 rpm by 60 multiplied by 2 into pi. So within bracket and average. So whatever be your expression be, you have to keep it in parenthesis and take the average value. So write average. Okay, here. So you have to do it. Now address. So this is kilonewton meter. So this is in kilowatt, around 2.3 kilowatt. Okay. So output power is there. Now we have to add loss. First is copper loss. So click on variables. See this WCUS we just defined now. Click on WCUS, average of WCS. Okay. Address 240. It is in watt. Yes, 240 watt. Sorry, 249 watt. Now um, core loss will be there. So for core loss, first I need to show you one thing, then I will tell you. Go to result, right click, create transient report, rectangular plot, loss, core loss, and also solid loss, new report. Okay. See, core loss has a transient, or you can see that from 9 to 10 it is getting steady state. So if you I have run it for one cycle only. If you run it for two cycle, you could understand that after 9 it is getting steady state. Okay. So I have to take the average value from 9 to 10 only. If I take the whole average value from 0 to 10, so it would be a problem. It will give you erroneous value. So I'll take it from 9 to 10. So it is required. First delete this plot. Double click on this average CUS, WCUS. Okay. Go to loss, core loss. Now click here on range function. Here it is all. Click is this three dot specify range 0.009. Okay, 9 to 10 millisecond. Okay. Okay. Average is here, written here. Okay. Address at 20 watt. Now same way solid loss address 426 milliwatt. These all these things we need for this particular video. Okay. One thing to tell you, there should not be any optometrics. Okay, like there should not be any parametric setup or parametric simulation defined. And in setup, if it is not required, don't go beyond one cycle because it will take more time. Another thing, if there is no input from the field calculation, keep the field calculation off. Click none here. Okay, these are two things. It will save the simulation time. Okay, now save the uh, s- yeah, yes, save this file. Save this project. Saved. Now close this one. Now open Optislang. Click on click here on guided. Okay. So this will show you ANSYS EDT. One thing to just mention that you will not see ANSYS EDT if you don't integrate the ANSYS electronics desktop with uh, ANSYS Workbench or ANSYS products, and therefore ANSYS Optislang. Okay, so you have to integrate it. You can Google it that how to integrate. Okay, so after integration only you can get the this one ANSYS EDT symbol here. Anyway, so click on ANSYS EDT and go to that folder. Yes, where your project are there. So this one, click here, open. Okay, so this is here. Double click on the icon. Enlarge the screen, expand it. It is all under top table. Expand this one also. Okay, so at one part you are seeing that what are all the independent variables here, what are all the independent variables that you have defined in your Maxwell project. Only the independent variable that has direct value, those only will be considered for optimization. All the dependent variable you can't consider. It's one thing. So first, here under the variable that is the outputs, select all these things, drag them to responses. Okay, similarly, now you have to choose that what all independent things you want to uh, select as optimization parameter. Suppose this is BS0 slot opening, I don't want to change it, suppose, so I will not select. BS1 I want to change, BS2 also I want to change, maybe it is bore dia. Delta S, so it is current density of current density in stator. So it generally be constant. So I will not select it. DO, outer dia, shaft dia. This is pole embrace. Whatever parameter you want to uh, select as an input to the uh, optimization, you have to select those. So I am selecting some of them, okay, and I am dragging it to the parameter tab. Okay. Now one tedious job is there. It is what is required. It will you can recognize the variable in a better way. So therefore, just rename them. You see, there is a long name is there, but actually their names are short. Delete the previous parts and rename them. It is actually helpful. Okay, almost done. Yeah. Okay, it's done. Now click on here variables. Okay, now we have to create the variables. Add variable, rename torque. Okay, go at the right under the expression, double click here. Now see, all the responses are starting with the name Maxwell. Okay, so first start a parenthesis, write max max. Now find where is the torque. This one is, they see the moving one torque. Click here. Okay, start a square bracket. Okay, write 0. Go out of the parenthesis. Start a square bracket. Write 1. Enter. See under value, the value of the torque has come. Similarly, add variable. Right here output power, that is PO. Okay, under expression double click, start parenthesis max. So it would be, where it is, yes, this one. Yes, see, this is the expression. Click inside the parenthesis, start square bracket, type 0. Outside the parenthesis, square bracket 1. Enter. Now see, it has come in torque 2298.4. Sorry, in watt 2298.4. Add variable. Now it would be copper loss WCUS. The same way we'll do. Start parenthesis max. Uh, this one, square bracket 0, outside square bracket 1. Enter. This has come in again in watt. Fine. Add variable W core loss, uh, parenthesis max core loss, square bracket 0, outside square bracket 1. Enter. See, it has come in uh, milliwatt. Okay, so change it. Double click here, go at the end, divide by 1000. Enter. So it is now in watt. Add variable WPM, magnet loss. Okay, here parenthesis max, this on solid loss, square bracket 0, outside square bracket 1. Enter. See, this is also in milliwatt. So again double click here, outside by 1000. Enter. Now this is in watt. Now write efficiency. PFF here. Now write what is efficiency. PO by parenthesis PO plus WCUS plus W core plus WPM. Enter. You can see this is uh, 0.89, 89% efficiency, 89.4. Okay. Now select all these, drag them to responses. Okay. Now apply. Okay. Now you can see under wizards there are optimization wizard. Select it, drag it to in this parametric solver system. Release. Okay. Enlarge it. Now here, see whatever uh, parameters, optimization parameters you have chosen, you have to now tell the software that what is the minimum and what is the maximum range of that. These are the values that is there in the reference model. Okay, suppose it is 4.7. Suppose I want it to from 2 to 6. Okay. I want the bs to be from maybe 3 to 8. Okay. D maybe from 50. It is 96. So D from 50 to 120, 50, 60. Okay. Like that, you have to do all those things. I am not doing that. So, what would be the range that you have to judicially select? On these, many things will depend. If you have a large range, then um, there will be a yes. The maybe the efficiency of the optimization may be poor. Maybe if it is a small range, you may lose some sweet point. May be possible. So there are some constraints are there. Okay. So yes, there will be some balance of sorrow. So accordingly, you have to choose the upper limit and lower limit. Okay, so I'm not doing that for all these things. You could understand what you have to do. Next, now here you have to say what you want to do. First, I want to maximize the efficiency. So maximize means a objective. Okay, so this is our objective. Click here, objective. Name this efficiency. 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 Expression. What is expression? EFF. EFF is the expression. Criteria, what is that? Maximization. So I have to maximize the efficiency. Another thing is there. Click that also I want to maximize. Click on objective. Right here, torque density, Tden. Tden. What would be the expression? Expression would be torque by parenthesis do second pi multiplied by do square by 4 multiplied by L, pi d square by 4 into L. That is the volume of the machine. Okay, so torque by volume, that is torque density. I will want to maximize it. Okay, so these two things are there for me. Now it may happen that you want the um, torque ripple to be within a limit. So therefore you have to uh, select torque ripple, peak to peak torque ripple, or maybe peak to peak torque ripple by average torque as a percentage or per unit in your that torque table that you have created in the ANSYS file, and you have to include it in the responses. Okay, if it is so, you have to take a constraint here. Suppose you can take a constraint. So suppose I am just uh, I'm just for explanation I am saying, suppose WCUS, so less than something. Now it may be less than something or greater than something. Okay, less than what? Maybe less than 280. I want it. Okay, so it is showing that it is already 249, so there is a white color. So if I take it 240, see, it will be red. So currently it is 249, so it is not maintaining the constraint. Like that you can here do the permanent magnet volume. That volume should be less than like this permanent magnet volume. So it can be done like this. Okay, so yes, after all these things, after setting the objectives and constraints of the optimization here, click next. Now click here on manual optimizer selection, and here already evaluation your algorithm is selected. Click on that only. That's good. Next, do nothing here, finish. Now one more thing to do, double click here. It's fine, not here. Double click here, evaluation algorithm. Mm, just- okay. Yes, double click here on the on the uh, on this phrase evolutionary algorithm. Double click here, then you can find NOA here, maximum number of samples. Okay, here 500 means whatever model you have, that will be simulated 500 times. Within this much simulation only, it has to the simulation has to converge like that. If you can increase it, you can decrease it as per your choice. You have to set the number of simulations. Okay, you can make it to 200, 500, or whatever. 500 is a standard one. So okay, now if you hit run, it will start running. My recommendation will be first go to file and save current project, and save the project on the same folder where the ANSYS file was there. So it is OPT. Okay. Now if I hit run here, it will start running. I will not do that. Okay. It will take a long time to do 500 simulation. Rather, I will show you one simulated or optimized result that I have done for my other purposes. Okay. So this one. Okay, so this file is already optimized. Okay, now if you double click here on the post processing, you can see this kind of a window. Okay, where this is again torque density and this is efficiency on the first figure. So these are two conflicting parameters. Okay, therefore one Pareto can be formed here, and you can see one Pareto has been formed here. Okay, and there's this, and from the software it is showing that base design is 492. And what are the various parameters here, what are the performances are here. So I am just showing you this. Uh, by this thing, you can see the post processing or the see the result of the optimization. But what I recommend or what I do, it's not like this. Just close it, quit. Um, Double click on here, evolutionary algorithm, expand it, result design. Okay. So what I do, click here, Control A, right click, export. Okay. Just result, save, tab delimited. Okay. So all the datas are exported. Okay. Now if I open this one, double click here, it is in Excel. Okay. So just Control A, uh, data, text to column, delimited, next, tab delimited, next, generate, finish. So see, all these things are there. Like you can understand that all the tabs are here. Now you can see that some of them are not present. Okay, data are not there. That means for those things, for those things, um, your geometry was could not be prepared. Okay, for some combination of the dimensions, geometry was invalid. That's why the simulation file could not create the geometry. So that's why these are empty. Okay, now you can analyze those things. Analyze means whatever, like the way you want to get the optimization, like optimized file, that is up to you. Just I can show you one thing. So this is for my result. I have prepared the, see, efficiency and torque density I have taken and prepared the Pareto like this. Is a scatter plot, and I can choose on my own depending on my requirement. And not only that, you can do one more thing. You can maybe assign um, weightage, okay, or the cost function. You can prepare your own cost function, or you can prepare the weightage for every one thing, that is efficiency, core loss, whatever, torque ripple, torque density. Okay, you can prepare the weightage, and you can prepare a value, like, or an expression, normalized expression, and you can get the optimized design on your own. So these are the result of the optimization. Okay, this is the, so in a following a evolutionary algorithm, this result or this Pareto we have achieved. The selection of the best design, the selection of your desired design is up to you. uh, the way you want, you can do it. Okay. So, and it will obviously vary from situation to situation. Okay, so it is all of that optimization things. Okay, thank you.